Resolving power of grating. What is this resolving power of grating? The resolving power of grating is its ability, that is, the ability of the grating to resolve two spectral lines which have nearly equal wavelengths. What is this spectral lines means? For that, let's see this diagram. When white light is passed through the grating, each wavelength diffracts at different angle, and in the telescope you will see the spectrum. This is the first order spectrum. In the spectrum you can see blue line, this green line, orange line, red line, etc. These lines are called spectral lines. Actually, in the telescope you will see such lines, and such lines are called the spectral lines. You can see here in this case separate lines because there is a large difference comparatively between the wavelengths of these colors. But then what is the resolving power of this grating? If suppose there are two wavelengths which are nearly equal, there are two wavelengths which are nearly equal, then if that grating can resolve that nearly equal wavelength lines separately, then you can call it resolving power of the grating. So let us see the definition of this resolving power of grating again. Resolving power of grating is its ability to resolve two spectral lines which have nearly equal wavelengths. Then what is the definition of this resolving power of grating? Definition is capacity of the grating to form separate diffraction maxima of wavelengths which are very close to each other. Each color form a diffraction maxima and minima. That is, each wavelength form its own diffraction pattern, and in that diffraction pattern, you will see maxima and minima. So, resolving power of grating is nothing but the capacity of the grating to form separate diffraction maxima of wavelengths which are very close to each other. For example, suppose this is the diffraction maxima of one wavelength, and this is the diffraction maxima of the another wavelength. So two separate diffraction maxima is formed. So it is nothing but the capacity of that grating. Okay. Resolving power of grating is capacity of grating to form separate diffraction maxima of wavelengths which are very close to each other. Then resolving power R is given by lambda upon d lambda, where lambda is the average wavelength of that two nearly equal wavelengths and d lambda is the difference between these two nearly equal wavelengths. We already studied the Rayleigh's criteria. As per Rayleigh's criteria, two wavelengths are just resolved when central maxima of one wavelength coincide with the first minima of the other wavelengths. So when we can say that the two wavelengths are just resolved, we can say that two wavelengths are just resolved when central maxima of one wavelength coincides with the first minima of other wavelength, which is shown in this diagram. As you can see here, there are two diffraction maxima. This is a diffraction maxima due to wavelength say lambda 1, and B is the diffraction maxima due to wavelength lambda 2. Now here you can see that this diffraction maxima of wavelength A coincides with the first minima. This one is here in this case. This is the first minima of diffraction due to wavelength lambda 2, that is B. Or here also you can see. This is in this case, this is the first minima of A, which is coinciding with the central maxima of wavelength B or lambda 2, whatever you want to say. So when the central maxima of one wavelength coincide with the first minima of the other wavelength, then you can say that those two spectral lines or those two wavelengths are just resolved. Let us see in this diagram. In this diagram, what you see, there are the two central maxima, which is shown by the red color and the blue color. Now, the red color spectra is due to wavelength lambda 1, and the blue color spectra is due to wavelength lambda plus d lambda. And there are 2 points here. We are taking the 2 points P1. What is the point P1? So the point P1, let's write first about the point P1. The point P1, we get principal maxima, and that one is the nth principal maxima due to wavelength lambda. Okay, point P1, at point P1 we get nth principal maxima due to wavelength lambda. Then what is the equation for that, nth principal maxima? For the nth principal maxima, then the equation is A plus B sine theta n, because we get this in the direction theta is theta n. We get the nth principal maxima due to wavelength lambda in a direction theta 1. Let us write that in direction theta n. Then the equation is A plus B sine theta n is equals to n lambda, and this is our equation 1. We know the value of n is 0, 1, 2, 3, etc. But in this case, we are getting at point P1 n principal maxima. So value of n is capital N, because we get the n principal maxima there. Then equation for minima. We know the equation for minima. What is the equation for minima? Equation for minima. Equation for minima is n times a plus b sine theta is equals to n lambda. Let us say this is equation 2. This is the equation for minima. In this case, this n cannot have values such as 0, n, 2n up to nn, because if the n has these values, then we get the principal maxima. We are writing the equation for minima, which is n times a plus b sine theta is equals to n lambda. Then let's see the point P2. What we get at the point P2? At point P2, let's see. At point P2 over here, at this point over here, we get adjacent minima to the next, we get the first minima. At point P2, we get the first minima which is adjacent to the n principal maxima. This is the n principal maxima at point P1. And at point P2, we get the minima due to wavelength lambda. So at point P2, we get here in this case, this is the minima of the diffraction spectra due to wavelength lambda. The red one is diffraction spectra due to wavelength lambda. So at point P2, we get the first minima which is adjacent to the n principal maxima in direction. In what direction? Theta n plus d theta n. This angle is d theta n, this one is theta n. So in the direction theta n plus d theta n, we get the first minima which is adjacent to the n principal maxima. So at point P2, let's write that at point P2, we get first minima which is adjacent to nth principal maxima in direction theta n plus d theta n. Then what will be the value of this n? We know this is the equation for the minima. Then what would be the value of n? Because this minima is adjacent, this minima over here, this minima is due to wavelength lambda 1, and that is the first minima adjacent to the n principal maxima due to wavelength lambda. Then what would be the value of n? This n. This n cannot have these values. So then this n can have value nn plus 1. Okay, then rewrite the equation 2 for first minima, which is adjacent to nth principal maxima due to wavelength lambda. So this equation 2 we can write then as n into a plus b sine of, now direction is theta n plus d theta n. So sine of theta n plus d theta n, which is equals to n lambda. But n is this, nn plus 1. So that is equals to nn plus 1 into lambda. Let us say this is our equation 3. So we got the equation 1 for the n principal maxima which is at the point P1, and we got the equation for first minima adjacent to the n principal maxima by equation 3. But at point P2, it's not only the first minima due to wavelength lambda 1. At point P2, you can see here at point P2, we get the first minima due to wavelength lambda. But at the same point, we are getting n principal maxima due to wavelength lambda plus d lambda, this blue color. is n principal maxima due to wavelength lambda plus d lambda. So these two wavelengths, we are saying that the wavelength lambda and lambda plus d lambda are just resolved. And when we say they are just resolved, the maxima, central maxima, coincide with the first minima of the other wavelength. So in this case, the minima due to wavelength lambda coincides with the principal maxima due to wavelength lambda plus d lambda. So at point P2, we get maxima due to wavelength lambda plus d lambda. So here we get principal maxima due to wavelength lambda plus d lambda in direction. See the direction. Direction is theta n plus d theta n at the same point here. At this point itself, we are getting the nth principal maxima due to wavelength lambda plus d lambda. So the direction is theta n plus d theta n. In a direction theta n plus d theta n. That is, then the equation for that n principal maxima due to wavelength lambda plus d lambda is a plus b sine of direction is theta n plus d theta n, and that is equals to n lambda. But now lambda is lambda plus d lambda, lambda plus d lambda, because at point P2 we are getting the principal maxima due to wavelength lambda plus d lambda. Let us say this is equation 4. Then one thing, we will simplify this. Let us multiply equation 4 into n. N is the number of slits. So equation 4 into n, what we get? We get n times a plus b sine theta n plus d theta n is equals to nn into lambda plus d lambda, and let's say this is equation 5. See the equation 5 carefully. This is equation 5 over here. And see the equation 3. Equation 3 is what? N times a plus b sine theta n d theta n is equals to nn plus 1 into lambda, where we get first minima due to wavelength lambda. And at the same point, we get n principal maxima due to wavelength lambda plus d lambda. So let us compare the equation 3 and 5. So this LHS is equals to this LHS, n times a plus b sine theta n d theta n. Here also same thing. So right side should be same then. So if the right side is same, then what we can write? Nn plus 1 lambda, this one, and that is equals to nn into lambda plus d lambda. Now let us simplify this. Nn, let us multiply it by lambda to each one. So nn lambda plus lambda is equals to nn lambda plus nn d lambda. So in this case, this nn lambda cancels with this nn lambda, and we get lambda upon d lambda, which is nothing but the resolving power. So lambda upon d lambda is equals to small n into capital N. This small n is order. capital N is number of slits. So from this equation you can see that the R, which is the resolving power, this resolving power increases with increasing order and with increasing number of slits. Number of slits are capital N. So what we'll get when, let's say, when n equals to, when this order is equals to 0, zeroth order. For zeroth order, resolving power is 0. So this zeroth order wavelengths are in zeroth order, wavelengths are indistinguishable. Indistinguishable. So here, in this diagram here, this is the zeroth order. So at zeroth order, the wavelengths are indistinguishable. Let us say if n equals to number of slits equals to 500 or 5000 and order is 2, then what would be the resolving power? Resolving power is what? Is equals to n into n. That is 5000 into 2, that is 10,000. So resolving power is 10,000.